Welcome to Ask and Learn.
We want to produce a graph of f is equal to x to the 6th minus 5x to the 5th plus 25x cubed minus 6x squared minus 48x. And we want to make sure that we include intervals of increase, decrease, extreme values, intervals of concavity and inflection, and we're going to use the first and second derivative graphs to do this as well. So this first graph here on the left is just of f of x as soon as I plugged it into my calculator. So it doesn't really tell us much about the graph at all, unfortunately. But with a little bit of help from our first and second derivatives, we might be able to get a good window to view everything. So I went ahead and took the first derivative of this and plotted it as well. And I just pretty much expanded it out until I saw all the intercepts. And so here we have 1, 2, 3, 4, 5 intercepts. So since it's a fifth degree polynomial, we know that satisfies everything that we need. Now, I went ahead and labeled these points here because they also want us to find where the function is increasing and decreasing. So remember, when f prime is strictly larger than 0, the function will be increasing. And now we can go ahead and say that. So let me go ahead and zoom out a little bit to give some more space. So the function is increasing, or f prime of x is strictly larger than 0 on, so it would be between negative 1.307 to negative 0.839. And let me just actually go ahead and scoot this all the way over. And then union that with, so then we become positive again at x is equal to 1. So 1.06, 2, then 2.505, and then union that with our interval after 2.748 to infinity. So that is where our function is increasing, and we will know the function is decreasing on all the other intervals, or when f prime is strictly less than 0. So that would be to the left of our first point, so negative infinity to negative 1.307, union negative 0.839 to 1.06, union 2.505 to 2.748. So now if we look at this, so it's our first point here, well, it's decreasing. So it's decreasing into that point and then increasing after. So this here is going to be a minimum. At the next one, it's increasing and then decreasing after. So this here is going to be a max, a local max. And following the same thing, the next one is going to give us a minimum. And then we're going to get a maximum and then a minimum after that. All right. And remember, that's just by using the first derivative test. Now, let's go ahead and look at our second derivative here. And so just like before, to get that viewing window, all I did was zoom out until I saw I had 4 roots, because all I really care about is where the function is positive and negative. All right, so this here is going to be concave up when it is positive. So up is when f double prime of x is strictly larger than 0. So to the left of negative 1.1, it is positive. So it's negative infinity to negative 1.1 union, and then 0.08 to 0.08 to 1.718, and I'll go ahead and just put this underneath union 2.635 to infinity. And the function is going to be concave down when f double prime is strictly, not greater, but strictly less than 0. So that's going to be just the remainder of our interval. So negative 1.1 to negative 1.1 to 0.08 union 1.718 to 2.635. And for points of inflection, all we need to check to see is that it's positive on one side and negative on the other. So at our first point here, that does change concavity. Here we also change concavity, change in concavity, as well as change in concavity, just because we want to see where it's positive and then where it's negative. And if it changes from positive to negative or negative to positive, then we know we will have a point of inflection there. All right. Now, the next thing I went ahead and did was plotted all those x values, all of the x-intercepts for the first and second derivatives, because we know those are going to be important points. So these first handful are all either maxes or mins, local maxes or mins, I should say. And then the rest of these are our points of inflection. So I went ahead and plotted all of these, and I looked at our output values. So here you can see the window I ended up choosing. And the reason I chose this window is I looked at our x values. So my smallest x value ended up being negative 1.307. And our largest ended up being 2.748. So I at least wanted to get these values into there. So I just slightly chose something to the left of negative 3, or to the left of negative 1.3, just to make sure I got everything else in there. And then I let it go to 4, even though it was just to 2.7, because I also wanted to include this intercept here as well. And the y values, well, I just went to all the outputs of our important points, and I found the smallest being about negative 33. So I just went ahead and went slightly below that to negative 40. And then I looked for our largest value, which occurred at about 22, or actually 23 up here was our largest value. And I just went slightly above that one as well. So this here, I'd say, gets all the points of importance, and the little dots you see on our graph were all the x values. So either the maxes or mins or points of inflection. And so we can definitely see all the changes, whether it's change in concavity, max or min. So I would say this is a good viewing window for this.